Oh, sorry, I didn't see you there. I was in a deep state of equilibrium, at one with Mother Nature and in balance with the world. But here's a thought. What do Zen Buddhists and civil engineers have in common? They both believe in and strive for equilibrium. I'm Thomas Brady, and today we'll be talking about equilibrium within civil engineering. We will discuss concepts such as what is equilibrium, why is it so important, and where did it come from? Firstly, let us cover what exactly is equilibrium. Equilibrium can simply be defined as a state where opposing forces or influence are balanced. The principle of equilibrium is quite easy, being the sum of all actions acting on a structure should come to zero. Like my friend always said, the best thing about equilibrium is that nothing changes. Before Newton discovered equilibrium in 1686, Aristotle ascertained that everything has its natural place, which kept the world in check, such as rocks like to be on the ground, hence they fall, unless propelled by an external agent. 1800 years later, Galileo came into the equation by removing the sense of belonging somewhat that came from a natural place, in its place suggesting that objects move at a constant speed, including at rest, until they are forced to change. Newton then refined his theory with over 200 experiments, thus creating the famous laws of motion. The laws of motion, as we know them today, are: number 1, every object remains in a state of rest or uniform motion in a straight line unless the application of a net unbalanced force causes it to change its motion. 2, when a net unbalanced force is applied to an object, its acceleration is proportional to the size of the force and acts in the same direction as that force. 3, whenever an object applies a force to a second object, the second object applies an opposing force of equal size to the first. If we were to talk in terms of structures and civil engineering, the laws would state that 1, structures neither move nor do they accelerate. Hence, the velocity of a structure and all the components that make it are always zero. Therefore, the net force on a structure is zero. 2, the second law says that all forces applied to a structure are due to accelerating masses. Finally, the third law says that these actions by an external force acting on a structure are resisted by the reactions of its supports. That is why you must look out for the following incantation: the sum of F equals 0. By invoking this statement, it means that engineers have called the structure into equilibrium. Once a structure is known to be in equilibrium, working out the forces at a point within the structure is relatively simple from using the equilibrium equations. As we have already covered, a member of a structure is in equilibrium when it maintains a balance of force and moment. In order to be able to prove or test it, you need to know the force and moment equations, or simply put, the equilibrium equations. Here are the equilibrium equations. As can be seen from the equations of the sum of f of x and the sum of f of y, representing respectively the sum of x and y components of each force acting on the structure or member. M represents the algebraic sum of the moments of these force components about an axis that is perpendicular on the xy plane. In other words, the z-axis as passing through a point O. Now that we have covered what exactly the equilibrium equations are, it is also important to understand how to use them properly. The first step when looking at a structure or member, whilst trying to establish if it's in equilibrium, is to draw a free body diagram. If a member is selected, it must first be isolated from its supports and surroundings. All the forces and moments must then be drawn that act on it. Here is an example of a free body diagram. As can be seen, the forces that act on each end of the beam have been drawn. Note that each force in their respective directions is opposing each other. This is because, in order to be in equilibrium, each force in their own direction must be equal and opposite. Members can also be split to work out the forces internally. A diagram can be seen of this now.
That's the way it's gonna be, little darling. We'll be riding on the horses, yeah, yeah.
So there we have it, equilibrium in all its glory. To recap, equilibrium is defined as a state where opposing forces or influences are balanced. Secondly, Newtonian laws show us that everything must be in balance, with every reaction having an equal and opposite one. And thirdly, the equilibrium equations, along with free body diagrams, can be used to check if a structure is in balance. So that's all from me, Tom Brady. But like I always say, if you aren't at equilibrium, then you better be at equilibrium.